Hi, welcome to Computer Science Explained. In this video, we will talk about 2's complement binary numbers representation. To obtain a negative number from a positive number with the same magnitude, or in other words, with the same absolute value in 2's complement representation, we need to invert all bits and then add 1. For example, let's obtain negative 5 from positive 5. This is positive 5. Let's change all zeros to ones and all ones to zeros. As I said in the previous video, after this procedure, we get 1's complement representation. Now let's add 1 and we get 2's complement representation. Using this procedure, we can obtain all negative numbers except the smallest number, because the range of 2's complement representation is asymmetrical, from negative 2 to the power of n minus 1 to 2 to the power of n minus 1 minus 1. So as we see, the smallest negative number has no positive counterpart. For example, the smallest number is negative 8 for 4-bit 2's complement representation, but we have no positive 8. It's not a big problem, because we can use the weights model to obtain 2's complement representation of any number. In 2's complement representation, a weight of the most significant bit is negative. The weights of the other bits are positive. For example, for 4 bits we have weights 1, 2, 4 and negative 8 in MSB. Let's once again obtain numbers 5 and negative 5. But now using these weights. 5 is positive, so we don't need to take negative 8. We need to take 4. We don't need to take 2 because 4 plus 2 is greater than 5. And we need to take 1. 4 plus 1 equals 5. For negative 5, we need to take negative 8. Because it is the only way to obtain a negative number. We don't need to take 4, because negative 8 plus 4 is greater than negative 5. We need to take 2, because negative 8 plus 2 is less than negative 5. We need to take 1, because negative 8 plus 2 plus 1 equals negative 5. Now let's consider 8-bit 2's complement representation. We have a sequence of weights 1, 2, 4, 8, 16, 32, 64 and negative 128. Let's make 2's complement representation of the number 42. We don't need to take negative 128 because 42 is a positive number. We don't need to take 64, because 64 is greater than 42. We need to take 32. We don't need to take 16, because 32 plus 16 is 48, and 48 is greater than 42. We need to take 8, because 32 plus 8 is 40, and 40 is less than 42. We don't need to take 4, because 40 plus 4 is 44, and 44 is greater than 42. Next we take 2 and obtain 42. Of course, we don't need to take 1. Now let's make 2's complement representation of the number negative 42. We need to take negative 128, because negative 42 is a negative number. We need to take 64, because negative 128 plus 64 equals negative 64, and negative 64 is less than negative 42. We don't need to take 32, because negative 64 plus 32 equals negative 32, and negative 32 is greater than negative 42. We need to take 16, because negative 64 plus 16 equals negative 48, and negative 48 is less than negative 42. We don't need to take 8, because negative 48 plus 8 equals negative 40, and negative 40 is greater than negative 42. We need to take 4, because negative 48 plus 4 equals negative 44, and negative 44 is less than negative 42. Next we take 2 and obtain negative 42. Of course, we don't need to take 1. Now let's check this result with the previous algorithm. This is 42. Let's invert all bits and add 1. The results of the two different methods are identical. Now let's make a representation of a number negative 1. We need to take negative 128 because negative 1 is a negative number. We need to take 64 because negative 128 plus 64 equals negative 64, and negative 64 is less than negative 1. We need to take 32 because negative 64 plus 32 equals negative 32, and negative 32 is less than negative 1. We need to take 16 because negative 32 plus 16 equals negative 16, and negative 16 is less than negative 1. We need to take 8 because negative 16 plus 8 equals negative 8, and negative 8 is less than negative 1. We need to take 4 because negative 8 plus 4 equals negative 4, and negative 4 is less than negative 1. We need to take 2 because negative 4 plus 2 equals negative 2, and negative 2 is less than negative 1. And finally, we take 1 and obtain negative 1. Now let's check this result with the previous algorithm. Let's invert all bits and add 1. The results of the two different methods are identical. As you can see, we have all ones in the 8-bit 2's complement representation of negative 1. It's not just a coincidence. The sum of all but the last weights is 1 less than the absolute value of the last weight. So 128 minus 127 equals 1. Actually, this is true for any number of bits starting from 2. Let's check. For 2 bits, for 3 bits, for 4 bits, for 5 bits, for 6 bits, for 7 bits, and so on. Now let's consider what will happen if we repeat the algorithm of inverting bits and adding 1. This is number 69. We invert bits and add 1. This is number negative 68. Let's repeat the procedure. We invert bits of negative 69 and add 1. And as we can see, we obtain positive 69. Let's do the same in 4 bits representation for the number 7. and again, repeated procedure returns us to the initial number. This is true for all numbers except 0 and the minimal number, because these two numbers have no counterparts. We have no negative 0 and positive 8 in the 4 bits representation. Let's perform the procedure of inverting bits and adding 1 for 0. We have overflow here, and after ignoring overflowing digit, we obtain 0. Let's perform the procedure of inverting bits and adding 1 for negative 8. We obtain negative 8. Now let's consider the third method of converting positive numbers to negative numbers. This method is fast, but the least intuitive and comprehensible. First, rewrite all zeros starting from the right till first 1. Second, rewrite this 1. Third, invert all other bits. Let's make negative 80 from positive 80 using this method. We move from right to left, passing zeros until encounter the first 1. Then we rewrite all past zeros and the first from the right 1. Then we invert all other bits and obtain negative 80. Let's check this method with the method of inverting bits and adding 1. We invert all bits of 80, then add 1, and obtain the same result. Thanks for watching. See you next time.